In this video, we want to sketch the graph of this rational function and provide the requested information. So in other words, we're going to give the domain, the range, the vertical asymptotes, if any, horizontal asymptotes, if any, and the intercepts of the graph. Okay, so you'll always want to make sure that your graph, or the function, I should say, is in simplified form. So in this one, I'm going to factor the denominator. Got a difference of squares. So that's x squared minus 4 factors into x minus 2 and x plus 2. So let's look at the domain first. When you have a rational function, solid in this case for the function for f of x, or it could be a y here instead of an f, the only thing you have to look at to determine the domain are there any numbers that make the denominator 0. We know division by 0 is undefined. So you can see I have a factor of x minus 2 here and x plus 2. So this first factor is 0 when x is 2. The function is undefined there. Second factor, x plus 2, that's 0 when x is negative 2. So those are not in the domain. So it's all numbers except those. So I'll write the domain this way. There's a couple of ways to do it here, but in this case it's easier to just use set notation. So it's a set of all x such that x cannot be 2 and x cannot be negative 2, because those are the numbers that make the denominator 0. Now let's suppose the numerator had a factor of x minus 2 also, just to make sure you understand this. So if I had a factor of x minus 2 here, then x minus 2 and x minus 2 would cancel. This function would not be in simplified form. So actually the graph would have a hole in it because those divide out. And I bring this out to you is because the next thing we're going to find is the locations where the function has a vertical asymptote. The function will have a vertical asymptote for every value that makes the denominator 0, as long as it doesn't make the numerator 0. So if I did have this x minus 2 here, 2 makes the numerator 0 because of this factor and also the denominator. So I would not have a vertical asymptote there. But that's not the case here. We don't have this factor. But sometimes you will. So what you want to do then is this. The vertical asymptotes come from numbers that make the denominator 0, but not the numerator. And those, of course, are the same values for which the function here is undefined. So one vertical asymptote would be at x equal to 2, and the other one would be at x equal to negative 2. That's where the function is undefined. That's how you get your vertical asymptotes. Simply find the numbers that make the denominator 0, but not the numerator. Now for the horizontal asymptote, and remember, asymptotes in general are lines that a graph approaches, but the graph doesn't touch. Now a graph may cross a horizontal asymptote, but not a vertical, because that's where it's undefined. So how do we find the horizontal? The easiest way to do it is look at the degree. If the degree of the numerator is less than the degree of the denominator, then the x-axis, or the line y equals 0, that's the same thing, x-axis and the line y equals 0, would be a horizontal asymptote. So if I made this 2 here 1, if that were just x to the first over x squared minus 4, then I'd have a horizontal asymptote at y equal to 0. But I don't have that. So I'm trying to give you all the main scenarios. Now if the degree of the numerator and denominator is the same, in this case 2 and 2, then just take this coefficient here over this coefficient here, that's 1 over 1, and then the line y equal to 1 will be a horizontal asymptote. Horizontal asymptotes are like this, vertical asymptotes are like this, and you could have a slant asymptote where the graph approaches a slanted line, or also called oblique asymptote. That only happens though if the degree of the numerator is 1 more than the degree of the denominator. In other words, if this up here were a 3 and this were a 2, then you have an oblique asymptote. Okay, the next thing we want to look at is the intercepts. So the x-intercept is easy to find. All you do is replace the x by 0. So put a 0 where the x is. 0 squared is 0. In the denominator, 0 squared is 0. So we got 0 minus 4. 0 over minus 4 is 0. So if the x is 0, the y is 0. So in this case, it turns out that the x-intercept is also a y-intercept. Notice if I replace the y by 0 and solve for x, so let's put 0 where the y is, that's the f of x. What do we have here? We're going to have 0 is equal to this. So for what value of x is this fraction 0? Well, denominator can't be 0, so the only way the numerator can be 0 is if x is 0. So the intercepts, in this case, 0, 0 is an x and a y intercept. Okay, so we have the domain there. We won't get the range yet. We'll do the range when we get to the graph. So we got then 0, 0 is an x and a y intercept. So that's all the information here, except we don't have the range yet. We could get the range by solving for x, but this one's a little bit more difficult to solve. I think I did one like that in the other video. So here what we do is we'll look at the graph. So let me clear this here. And let's look at the graph. What we're going to do for the graph. So on the number line, what I'm going to do is I'm going to plot the zeros of the numerator. It's what number makes the numerator 0? Well, 0. That's 1 0 right there. And the zeros of the denominator were -2 and 2. Those, of course, again, were the locations of the vertical asymptotes. Now the next thing that I look at is using these values. Just call them zeros in general, zeros of the numerator and zeros of the denominator. We want to look and see where the graph is above the x-axis. But first, let's go ahead and draw the equations of the vertical asymptotes. So there's one there at x equal to 2, and one at x equal to -2. And then we have a horizontal asymptote at y equal to 1. Okay, so negative infinity on this number line is positive infinity, I should say. It's over here somewhere to the right. And negative infinity somewhere to the left. And just so you can see it more clearly, let me factor this again. It's x minus 2 and x plus 2. So I want to know whether the graph is above or below these intervals here. From 2 to infinity, from 0 to 2, from -2 to 0, from negative infinity to -2. All we have to do is just pick a number. So let's pick a number larger than 2, say 3. Okay, put 3 here. 3 minus 2 is positive. 3 and 2 is positive. The numerator is squared, so that's always going to be positive. So this is a positive here. Between 0 and 2, I want to pick 1. 1 minus 2 is negative, times the 1 and 2, that's positive. So it's negative in the bottom. The numerator is always positive, so this will be negative here. Pick a -1 to the left of 0. This is my negative. To the left of the -2, let's pick a -3. -3 squared. -3 squared is 9 minus 4. That's a positive, so in here it's a positive. So in the interval where you have a positive, that tells you that the graph is above the x-axis. Where you have a negative, it tells you it's below. And remember, the only intercept we had was 0, 0. We didn't have a y-intercept. Well, actually, this is the x and the y-intercept, but those are the only ones. So here's what we know. We know the graph passes through 0, 0 right here. We have a vertical, and these are a little bit off here, so couldn't draw them that straight, but close enough. X equal -2 is one vertical asymptote. X equal 2 is another one, and of course you have the horizontal line here is the horizontal asymptote passing through 0, 0, 1. I'm going to start on the right side of this. I have a plus to the right of the vertical asymptote, so that tells me the graph has to stay above the x-axis. So that means it has to approach this vertical and this horizontal. So the only way that could happen now, it could go like this from the bottom, but we don't have an intercept there. So the only option we have is we draw it this way. And remember, these lines go on forever. So arrows this way, arrows this way. This goes on forever this way, and the same way over here. And the line approaches the vertical. It never crosses the vertical. Again, I want to mention to you, in some cases, the graph will approach a horizontal. In this case, it doesn't. And I'll show you how you can confirm that a little bit later on. Now, the next thing is between 0 and 2, that have a negative, so that the line goes below the x-axis. So let's start at 0, 0. And to the right, it's negative, so it comes down. So, and then, of course, you have a vertical asymptote there. It's just to draw it so it approaches. So it goes down like that forever. And then between negative 2 and 0, I have another negative. So this comes down also below. And draw it so it approaches the vertical. Now what do we have? Okay, to the left of negative 2, I'm up here. Positive, it's above. So you draw the graph so it approaches the vertical and approaches the horizontal. Obviously it can't go down here because there's no intercept. So the graph is going to look like this. And there you have it. So we set the domain. The domain was a set of all x except 2 and negative 2, which also gave me locations of the vertical asymptotes. The vertical were x equal to 2 and negative 2. Horizontal asymptote was y equal to 1, and the intercepts, we had one that turned out to be a y and an x intercept. 0, 0. There you have it. The only thing we need here is the range. So let's look at the graph. This little parabola you see down here at vertex at 0, 0, it goes down forever. So that includes all the y's down on the negative side. And then the graph stays above the line y equals 0, the horizontal line. So we could say then that the range, it doesn't include the 1, because y equal 1, that's your horizontal asymptote, because the graph approaches it but doesn't touch it. So I'll draw the range this way. It goes from, starting from the bottom, negative infinity to 0, because the highest point in this area here, this section here, is 0, 0, and then it goes down. So negative infinity and 0, and then union. And then you can see now for the y value, it stays above the 1, y equal 1. That's the horizontal line, y equal 1. So this is going to go like this, 1, and then it goes above. The graph stays above the line y equal 1. So now I mentioned that the graph is never going to cross a vertical asymptote because that's where it's undefined. It may cross a horizontal. In other words, you could have something that looks like this. The graph could be go like this and then come down and never touch again. It crosses here, say, in some cases, but never touches again. So that's still considered a horizontal asymptote. The thing about it is, how do you know that it doesn't cross? Let's say consider this section right here. How do we know that it doesn't go like this and then it comes down, crosses, say, right there, and then it comes back up and never touches again? If it does that, that's still considered a horizontal asymptote. But how do we know that it does or doesn't do that? Sometimes it's just common sense based on the graph. But you can do this also. We got x squared over x squared minus 4. If the graph crosses the horizontal, then you should have a solution to this, y equal to x squared over x squared minus 4. You should have a solution to that equation. So do we have one? Well, let's multiply both sides by x squared minus 4. On this side, the x squared minus 4 cancels. It just leaves me with x squared. Does that equation have a solution? Well, notice the x squared and the x squared cancel. So I get minus 4 is equal to 0. That's impossible. Negative 4 cannot be 0. That's one way to do it, or to determine if a graph crosses a horizontal asymptote. Never going to cross the vertical, but in some cases it may cross the horizontal. Thanks for watching. We'll see you next time.